the plan of the talk is to just share a combinatorial construction associated to partitions and positive numbers. So, yeah, you go ahead. So, let us fix a positive integer n throughout. A partition with n parts, with at most n parts, is for me a sequence of non-negative integers that are weakly decreasing. Okay. So, you can visualize a partition as a Young diagram. How do you visualize? You draw, so 3 boxes. So, for the partition 3, 2, 2, 0, you draw 3 boxes in the first row, 2 boxes in the second row, 2 boxes in the third row, and 0 boxes in the fourth row. Okay. This is called the Young diagram associated to the partition 3, 2, 2, 0. Okay. So, when you have two partitions, one contained in other, by that I mean the Young diagram of one contained in the Young diagram of the other, we can talk about skew shapes, which is you delete the boxes of the smaller partition from the boxes of the bigger partition. Okay. So, there are these special skew shapes called rim hooks. So, a rim hook is a connected skew shape that does not contain a 2 by 2 box. So, what I mean by a 2 by 2 box is, for example, look at this skew shape. This is the partition 3, 3, 3 minus the partition 2, 1, 0. It has a 2 by 2 box. So, this is not a rim hook. I mean, this is not a rim hook, yes. And connected, by connected I mean you should be able to go from one box to any other box through a chain of boxes that share a common edge. So, for example, from this box to this box you can go like this, but here from this box to this box you cannot go because there is no box that connects this box to this box and shares edges. Is that clear? Okay. So, a rim hook is sometimes called as a ribbon also. So, by a ribbon I mean a rim hook. By a T rim hook I mean a rim hook which has T boxes, right. Okay. So, here are some small rim hooks. So, all 2 rim hooks look like this. They are either 2 boxes stacked one upon the other or 2 boxes placed one next to the other. So, that the set of all 3 rim hooks are this and the 4 rim hooks are this. So, now comes the definition of T core. So, let us fix a positive integer T, and given a partition, what is the T core of the partition? So, what you do is you draw the Young diagram of the partition and you successively remove T rim hooks from the partition until all the T rim hooks are exhausted. For example, consider this partition 4, 2, 4, 4, 4, 2. You draw the Young diagram 4, 4, 2, 4, 4, 4, 2, and then you remove, let us say, this rim hook, and then you remove this, you remove this, and then you have no more rim hooks to remove, no more 3 rim hooks to remove, and there you go, you have the 3 core corresponding to the partition 4, 4, 4, 2.
So, why can't I remove the rim hook on the upper left corner first?
Exactly. So, you can
No, on the corner top left.
right, yeah. Good point. So, while you remove a rim hook, you cannot remove it arbitrarily. You have to, after you remove it, it should still continue to be a partition. It should be a Young diagram corresponding to a partition, right. So, yeah. So, for example, you cannot remove these 3 because then what figure you will have will not be a Young diagram of a partition, right. There will be a gap here and there will be 2 boxes here. That is not allowed. Yeah. But the next question that comes here is you can remove rim hooks in different orders. Why should the residue be the same, meaning that the T core should be the same? That is something very strange. I will try to answer that question. So, for example, in this for this partition you can remove, so all these vertical shapes are 3 rim hooks. Now, you can remove these one by one, and then you again remain with the same residue, the same partition after removing. But why are they same? So, for that we introduce there is something called a beta set associated to a partition. Okay, so the beta set is basically what you do is, we are given a weakly decreasing sequence, you can construct a strictly decreasing sequence out of it just by adding the staircase partition of n corresponding to it. So what is the staircase partition? The staircase partition is the partition n minus 1, n minus 2, n minus 3 dot 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 up to 0. So this is indeed a bijection between the set of all weakly decreasing partitions and strictly decreasing sequence of positive integers, non-negative integers. Yeah, once you take the, once you write out the beta set of the partition, you plot the beta set in what is called a T abacus. So these T abacus is it consists of T many strands where there are beads, and the beads are numbered like this 0, 1, 2, 3, 4, 5 like that, and then you just put a bead for every number in the beta set. For example, for the partition 4, 4, 4, 2, the beta set is 7, 5, the beta set is 7, 6, 5, 2, right? 4 plus 3, 7, 4 plus 2, 6, 4 plus 1, 5, 2 plus 0, 2, and you record it here. So 7 is this, 7, 6, 5, 2. So what is the point of constructing the T abacus? So the removal of T rim hooks has a straightforward interpretation here. So when you remove a T rim hook, it corresponds to moving a bead one step up in the abacus. So look at this bead here. This abacus was for the partition 4, 4, 4, 2. So if you remove this rim hook, you will have the partition 4, 3, 2, 2, and the three abacus corresponding to this partition differs from the previous one by just this bead. This bead moved one step up. So all possible ways of removing rim hooks from a partition, T rim hooks from a partition, is all possible ways of moving beads up in the T abacus. So in any way you move up, you are going to end up in the same state, and that, yeah.
How do you decide which bead to move?
No, that is, you are free to move any bead.
So from the left hand side, how to determine which bead?
That I don't know. Yeah. Right. So a closely related construction is what is called the T quotient of a partition. So a T quotient is read off from the abacus as follows. You consider each strand and number it from top to bottom by 0, 1, 2, 3 and so on, and then go back in this bijection. Go back in this bijection so that you will get partitions associated to each strand. So for example, here the beta set that you get will be just 0, 1, 2, just 2, right? And then if you go back in the bijection, you are going to get just the 2, and the partition is 2 here. Here the beta set is 1, 0. If you go in the bijection, you will get 0, 0, which is the empty partition. So this is called the T quotient of the partition, of the partition lambda. So why these T cores and T quotients? They come up everywhere in like they originally came up in modular representation theory of symmetric groups. They also come up in symmetric function theory. For example, I happened to work out a generalization of a theorem by Littlewood, which says that if you consider the Schur polynomial associated to the partition lambda, and if you twist the variable set by its tth root of unity, then this polynomial on the left hand side factorizes as a polynomial, factorizes as a product of Schur polynomials where the indices are the T quotients when the T core is non-empty. If the T core was not the empty partition, then this specialization gives 0. Yeah. I'll stop here. These are the references.
We have time for 1-2 quick questions if anyone has.
So I have a very general question. I've heard about Ramanujan's theory of partitions and its use in string theory. Is there any relevance of what Ramanujan did in what you do?
I don't know.
Ramanujan is also known for partition theory.
Right.
So the left hand side is a priori a polynomial in x to the 1 by t.
Right.
But it turns out to be a polynomial in
X, yes.
So let's thank the speaker again.